Hello, everyone, and welcome to the first session of our four-part webinar series, Fundamentals of Connection Design, presented by Brad Davis. Today is October 23rd, 2019. My name is Nate Gonner with AISC, and I'll be your moderator for this webinar series. I would like to introduce our speaker, Dr. Brad Davis. Dr. Davis is an associate professor of civil engineering at the University of Kentucky, where he is responsible for all steel design coursework and has received excellence in teaching awards. As the owner of Davis Structural Engineering, he provides consulting services for structural vibration, steel connections, and advanced steel design applications. Dr. Davis earned his PhD from Virginia Tech and has 8 years of experience in building design. He has SC and PE licenses in approximately a dozen states. He is a member of the AISC Committee on Manuals and Textbooks and a consultant for the Steel Solutions Center. He has published approximately 24 journal and conference papers on vibration and has presented a number of continuing education courses on vibrations and steel connections. We're happy to have him here today to talk about steel connections. So Brad, thank you very much for being here, and I'll now turn the floor over to you.
Okay, thanks Nate. And I want to start the series by thanking AISC for this awesome opportunity, and I really hope the participants all find the material useful. And I also want to thank Dr. Thomas L. Murray for all of his instruction over the years, and also for giving me a really good head start for this webinar series. Finally, thanks to all the participants for being here. Okay, you can see our schedule on this slide. We will have two sessions on fundamental concepts of connection designs. And then we will have 2 sessions on shear connections. So fundamental concepts, part 1. Okay, today's topics are going to be these: reference documents, nomenclature, steel properties, connection types, classification of beam to column connections, limit states and load paths, bolt-related limit states and detailing, and finally fillet weld-related limit states and detailing. Okay, so let's start by talking about our reference documents and go through some nomenclature and the steel properties that we're going to be using. Okay, so our 2 primary reference documents for our entire series will be the AISC or ANSI 360 document, specification for structural steel buildings, 2016 edition. We'll be spending a little bit of time with Chapter B and D, and a lot of time with Chapter J. Also, we will spend a lot of time with the AISC Steel Construction Manual, 15th edition, the Blue Book. We'll mention several times the Research Council on Structural Connections, or RCSC, specification for structural joints using high-strength bolts, 2014 edition. Finally, the AWSD 1.1 is a very important document for steel connection design. I'll just mention it there, although we won't be referring to it. Okay, you can see the cover for our primary references. Here's the specification for structural steel buildings. Of course, this is our steel construction manual, and there's the cover for the RCSC specification. Now, the RCSC specification is of course in part 16 of the manual, right behind the specification for structural steel buildings. For brevity's sake, we will be referring to these documents as, in this case, the specification or spec, manual or RCSC specification or spec, or both. Okay, so in the AISC manual and specification, there are 2 different design methodologies. The first is called load and resistance factor design, or LRFD. And with it, our design, or when we check a limit state, we must satisfy this design inequality. And R sub U must be less than phi times R sub n. R sub U in this case is the required strength that's derived using LRFD load combinations, and those are going to come from ASCE 7. Phi is the resistance factor. R sub n is the nominal strength for this limit state, and roughly speaking, that's the best prediction of the actual strength. Phi times R sub n is called the design strength. It's the available strength generically, or design strength particular to LRFD. Okay, so the second design methodology is called allowable strength design, or ASD, and here's our design inequality for that. In this case, the required strength using ASD load combinations, R sub A, can't exceed the allowable strength, R sub n divided by omega. Now again, here we have the same nominal strength that we used in the LRFD design methodology. So it's pretty effortless nowadays to switch back and forth between ASD and LRFD using these modern formulations. Okay, so just emphasizing the nomenclature, generically in the AISC specification or manual, it's this. It's that the required strength must be less than or equal to the available strength. If you get specific for LRFD, we have the required strength using LRFD load combinations, and that can't exceed the design strength. Specific to ASD, we also have required strength, but now due to ASD load combinations, and that can't exceed the allowable strength, R sub n divided by omega. Okay, we're going to be using load and resistance factor design for our entire webinar series. So let's talk about the resistance factors for a minute. The resistance factors are intended to account for inevitable uncertainties in the strength prediction. They are not there to account for design errors or construction errors. Okay, so in steel connection design, we very often have one of two phi factors. We have phi of 0.9 for ductile limit states, and an example of one of those is tension yielding. And with these, they're pretty easy to predict fairly accurately and precisely, so we really don't need to reduce R sub n very much to get to the design strength. So we have a phi of 0.9. A lot of the others are non-ductile limit states. They're more difficult to predict, and the predictions are less precise. So we need a larger margin. So here we use a phi of 0.75. An example of one of these would be tension rupture. Now there are a few other phi factors, but these are most of those. These are used in most of the limit states in connection design. Okay, let's talk about the steel properties that we're going to use, and I've tried to use the ones that I think we will be using moving forward. For plates, we're going to use A36 steel, and the yield stress for that is of course 36 KSI, and the F sub U is 58 KSI. Okay, for angles, the manuals committee recently approved using 50 KSI in our work, so we're going to switch to 50 KSI angles here. So we're going to be using A529 grade 50 steel. The yield stress for that grade is 50 KSI, of course, from the grade name, and the tensile strength F sub U is 65 KSI. Okay, for beams and columns, we have our familiar A992 steel. Now, in many of our limit states, we're going to be checking either shear yielding or shear rupture. So we need a shear yield stress and a shear rupture stress. So we take the corresponding uniaxial value, Fy or F sub U, and multiply by 0.6 for both of those. Okay, so what are the connection types? We can break these into four pretty good sized groups here, broad groups of tension connections, compression connections, shear connections, and moment connections. So let's see the different kinds of these, some examples. So for tension connections, we have several examples on this slide. Here you have a T-hanger. Imagine this angle is in tension. So this is a tension connection. Now, in this case, we have prying action on these bolts that we need to consider. Here's a plate hanger. Imagine this angle is in tension again, so we have a tension connection here. For this truss, imagine that this web member is in tension, so we need a tension connection right there. course, here's a pretty cool picture of a heavy bracing connection. Now, lots of the connections, especially in our webinar series, will be what we call directly loaded. They're simple connections such as these, and the main design assumption here is that the T sub U in this case is equally resisted by the bolts. Okay, compression connections. Three main kinds of these. We have column splices, we have beam bearing plates, and column base plates. Of course, the beam bearing plates or column base plates are on masonry or concrete. We're going to be spending a lot of time with these two in session number 2. So simple shear connections. There are a lot of those in a typical building, and these are the types in the manual. We have double angle connections, single angle shear connections, single plate shear connections, also sometimes called shear tabs, shear in plates, and we have two kinds of seated connections, and then we have T connections. So let's see some pictures of those. On this slide here, you see a double angle connection where the angles are welded to the beam and bolted to the supporting girder in this AISD teaching sculpture. Here's a single angle connection that's bolted to the beam and bolted to the supporting girder, and you have to just take my word for it that there's no angle on the other side. Note in these sculptures, the bolts that are painted, like these, are the ones that would be installed in the shop, and the unpainted ones are the ones that would be installed in the field. Okay, single plate connections. In this example, you can see that there's a plate that's just welded to the girder, and then a beam web bolts to that plate in the field. Here's another example of a single plate shear connection. There are 2 of these, and they're at this HSS column. And note that the single plate shear connection is especially useful at HSS columns. Okay, here's a shear in plate. In this case, we have a typically fairly thin plate that's transverse to the web and fillet welded on both sides to the web and then bolted to the girder. Here's a T connection, and you can see that the flange is welded along the edge there, and the stem is then bolted to the supported beam. Here's an unstiffened seat connection. You just see an angle there. And here's a stiffened seat connection. So we have a seat plate and then a seat stiffener there. All right, now moment connections. We have these 5 categories in the AISC manual. We have flange welded moment connections, flange plate welded or bolted moment connections, T-stub moment connections, flange angle moment connections, and moment in plate connections. Okay, and here you see an example of actually 2 flange welded connections. Here we have a beam that's framing into the flange of the column, and each flange of the beam has a complete joint penetration weld to the column flange, making a moment connection. Here also we have a beam framing into the web of the column, and each flange of the beam has a complete joint penetration weld to the column stiffener at the bottom there and at the top there. So we have a weak axis moment connection there, or moment connection into the weak axis of the column. Okay, here's a flange plate bolted connection. These plates are probably welded on in the shop, and then the connection is bolted up in the field along there. There's a T-stub moment connection, and then a flange angle moment connection. All right, here's a couple of pictures of moment in plate connections. This one's a flush moment in plate connection, and you can see that the plate does not extend above the top of the beam nor below the bottom of the beam. So all of the bolts are in here. Okay, this one is an extended moment in plate in which the plate is extended down far enough to get a couple of bolts there and up far enough to get a couple of bolts here. So now we have 4 bolts minimum. We can have more than 4 at each flange. So of course this is a much stronger and stiffer moment connection than our flush moment in plate. All right, so now we have these various kinds of connections. Now zooming in on beam to column connections, we need to be able to classify these. And we have 3 classifications that are used in the manual. First we have fully restrained or FR moment connections, partially restrained or PR moment connections, or simple shear connections. So we need some way to know which one we have for a particular connection. There are various classification schemes. Let's talk about the one that's in the AISC manual. Okay, let's start with this diagram here, and we have a column there, and a beam, and it has some kind of a connection. As we load it with, in this case, a uniform load, we will develop some end moment in the beam due to the connection restraint, and we will have some end rotation theta that will be induced. Now we can plot this M versus theta here. We have the end moment this way, and the rotation on the x-axis. Now, in the extreme cases, let's go to one end of the spectrum. On one end of the spectrum, we have a simply supported beam with a pin and a roller. Of course, the moment is 0 at the end of the beam, and we have the simply supported beam end rotation theta sub s. Now, we can plot that point right here. This is theta sub s and a 0 moment. Going to the other end of the spectrum, we have a fixed beam with the same load, and we have 0 rotation, and we have the fixed end moment there. We can plot that point right here. Okay, there are two key points. Oh, yeah, and by the way, we can draw a line between this point and down here, and that's called a beam line. Of course, there's an infinite number of beam lines depending on the magnitude of the uniform load that's applied here. Okay, there's a couple of key points on this plot. One is here at 0.8 theta s and 0.2 m sub f. And any connection with a moment rotation curve that goes below this or at this point is called a simple shear connection, and we're going to model those as pins for the connection and the beam design. And there's our simple shear connections. There's a second point up here at 0.1 theta s and 0.9 m sub f. And any connection that has a moment rotation curve that squeaks in above that point is a fully restrained moment connection. And we're going to idealize those as rigid connections between the beam and column for our design purposes. Of course, everything in between is a partially restrained moment connection. So which ones of our connections qualify for each of these? Okay, so first, for FR moment connections, fully restrained, these four: flange welded, flange plate welded or bolted, T-stub, or moment end plate. Those are four that we're going to design as fully restrained moment connections. Okay, how about partially restrained? They're PR moment connections. A flush end plate can be one of those if it's not designed properly in the design guide 16. We can also have flange angles and double angles that can be used for partially restrained moment connections. Okay, simple shear connections, we have these 6: double angles, single angle, single plate, shear end plate, and the two kinds of seated connections that are in the manual. And finally, T-framing connections. So these 6 we're going to design to qualify as simple shear connections. Okay, so as we design connections, we need some way to identify the limit states and just to think about the design as we're going along. And the most useful way to do that, I think, is to envision the load traveling from one beam to the other through the connection. Try to visualize what limit states we would have, and then check them as we go along. So let's see how this approach works with this simple directly loaded tension connection. In this case, we have double angles, and they're bolted to a gusset plate over here, and then this gusset plate is finally welded to a support at the left side. Okay, so using this recommended approach, we want to envision the force traveling from about here in the double angles through the connection and ending up over here in the support. So let's see how that works. Okay, so starting on the right side of this connection at section number 1, the only thing that can happen here is angle tension yielding. And really, this is a member design limit state, but it's a very good warm-up for connection design, so that's a great place to start there. Okay, moving to the left, at section number 2, we have angle tensile rupture. And in this case, we will have shear lag effects that we will get into later in session 2. Okay, moving to line 3, L shape there. We have block shear that can happen there on that plane. Okay, finally, along number 4, we have a newly explained limit state that we're calling shear transfer. And this is a combined limit state. We are combining 3 checks that we used to do in the traditional methods before into one. So we're going to be checking angle, bearing, and tear out. So there's 2, and then bolt shear rupture. There's 3, and then plate bearing and tear out. So there's so then we have 5 of these total. Now we have all those or we have 3 limit states we used to check. We're boiling them down into one check here. It's a bigger check, but we have 1 check there. Okay, so now once we have transferred this load into the plate, we have at this section 5 we have plate tensile rupture. Section number 6 we have plate tensile yielding. Finally, moving the load over to here, the next thing that can happen would be weld rupture to the support, so we need to check that. Finally, if we knew more about the support, we would probably have some limit states there. Imagine that if this is framing into a column flange, we probably have column web yielding there. Finally, one more remark on plate block shear. Block shear generally applies, but in this case we would not check it because we only have 1 line of bolts and they're right in the center of the plate. Okay, so let's talk about basic bolt-related limit states and detailing. Okay, so what are the kinds of bolts that we see in the AISC manual? First, we have A307 machine bolts. They have a tensile strength of 60 KSI. And then we have 3 groups of high-strength bolts. Group A, high-strength bolts, have a tensile strength of 120 to 125 KSI. And in this group, we have ASTM F3125 grades A325 and F1852. We also have ASTM A354 grade BC. Okay, in group B, they're higher strength bolts. We have ASTM F3125 grades A490 and F2280. And finally, we have ASTM A354 grade BD in group B. Next, we have the very high strength or super high strength bolts, and in this group we have ASTM F3043 and F3111. Okay, and we know that this last group is not currently readily available. Maybe it will be soon. Okay, so these bolts, see some pictures of them here. They use heavy hex heads, like shown here. And we want to just mention here that the thread length is a function of the bolt diameter. It's not a function of the bolt length. And you can look in table 7-14 for the thread length for various diameters of bolts. For the thread length as a function of the diameter of the bolts. Okay, you notice in this table, or on the slide a couple of slides ago, we mentioned the F1852 and 2280 bolts. Those are twist-off bolts like these that are used to achieve proper pretension. Now we'll talk about that more in the tightening section in a few minutes. Okay, so now with that, what are the connection types? We have about 4 kinds of connections. We see 3 of them here. First, we have bearing type connections, and we have 2 kinds of those. Then we have slip critical connections. So the bearing type connections, with that kind of connection, the bolts bear on the inside of the holes, so we're transferring the shear by shear stresses in the bolts. We have N type, in which the threads are included in the shear plane and have a weakening effect. Or we have X type, where the threads are excluded from the shear plane. So then we have the shear plane is at the clean shank away from the threads. Okay, we also have slip critical connections. In these, we are relying on friction to transfer the shear, not bolt shear. Okay, some example designations. We would call these, say, like a 3/4 inch grade A325-N. There's just an example call out for one of these. Or another example, 1 inch grade A490 SC for a slip critical connection. Okay, let's talk about bolt tightening. For bearing type connections, it's pretty simple. We just need to have the tightening to a snug tight condition. And per the RCSC spec, this means that we have the tightness that's attained with a few impacts of an impact wrench, like one of these, or the full effort of an ironworker using an ordinary spud wrench, sort of like this picture, although I think he could push harder than that if he sort of got over the thing a little more and pushed down. But in any case, the idea here is to bring the plies into firm contact. And that's all we must do for bearing type connections. Okay, it's a different story for slip critical connections. There's a lot more going on there. In this case, we're depending on the normal force from the bolts, clamping the connected parts together and thus causing this frictional resistance to the load. So we need to have a reliable interface between the connected parts. Okay, so for Class A, we need at least clean mill scale there. If we want to have Class B, we need actual fading surface preparation. And we're going to need field inspection for slip critical connections. Okay, because we care about the clamping force, we need to know what pretension we have. So we're going to have pretensioned bolts, and there are 4 methods listed in the RCSC specification: the turn of the nut method, calibrated wrench method, the use of direct tension indicator or DTI, or the use of twist-off bolts. There's actually a 4th kind of connection that I'll call just a pretension bolted connection. In this case, we just need the bolts pretensioned for some reason, but we don't need an SC connection. So we have the same pretensioning requirement, but we don't have any surface preparation or inspection like up here for the slip critical connections. Okay, let's talk about these pretensioning methods a little bit. First, the turn of the nut method. In this case, the nut is tightened to a snug tight condition, and then the nut is rotated through an additional angle theta. And the angle theta we get from the RCSC specification, table 8.2, and it's a function of the bolt length. The longer the bolt, the larger theta is. So for example, if we have a bolt length that does not exceed 4 times the bolt diameter D, then our theta is 1/3 of a turn. Okay, the calibrated wrench method. In this method, whatever tightening device that's going to be used, like this impact wrench we have here, will be calibrated on site using a device like this, a Skidmore-Wilhelm calibration device that reads the force up there. And once these wrenches are properly calibrated, they will shut off once they achieve the desired pretension. A direct tension indicator, or DTI tightening. With these, the washer is like this. They have these little nubs, for lack of a better term. And when the washer is tightened, or when the nut is tightened, these nubs get sort of flattened or squashed a little bit, and that will close this gap. And then a feeler gauge can then be used to determine whether or not the proper pretension has been achieved. These are called direct tension indicators because they're more directly measuring the pretension than if we were converting from torque to tension. Okay, finally, twist-off tightening. In this case, we have a picture of a twist-off bolt. And these kinds of bolts are installed, and then the nuts placed on there and tightened to a snug tight condition. And then a special tool is used that grabs this spline and nut and twists the spline relative to the nut until this spline breaks off due to the shear stresses along this line from the pure torsion. And once it does that, then the bolt is at the proper pretension. or at a pretension that exceeds the minimum value at least. Now, note that we need to make sure that, okay, we are relying on a certain coefficient of friction in here in these threads, so we need to take care of these bolts to guarantee that we have the correct surface on those when they're installed. Okay, bolt hole types. There are 4 kinds of these in the AISC specification and manual. First, we have standard holes, and oh, by the way, we go to the spec table J3.3 for these. For standard holes, if the diameter of the bolt is not exceeding 7/8 of an inch, then the standard hole diameter is the bolt diameter plus 1/16 of an inch. Okay, for larger bolts, we add 1/8 of an inch. Now this is new, and this results from some problems installing larger bolts in standard holes due to the bolt and hole diameter tolerances. Okay, we also have oversized holes, and the diameter of an oversized hole is the diameter of the bolt plus a distance ranging from 1/8 inch to 5/16 of an inch, depending on the bolt diameter. Slotted holes, we have short slots, and these are very popular. And the short dimension of these is the same as a standard hole diameter. And the longer dimension is going to be the oversized hole diameter plus a 1/16 of an inch. These are very, very commonly used. We also have long slotted holes. The short dimension of those is a standard hole diameter, and the long slot is a dimension that's up to 2.5 times the bolt diameter. For our course, our standard hole is going to be the default. So if we have holes there and I don't tell you what diameter or what kind of hole, that's what we're using. That's just the default. Okay, so let's take a look at a good example of the use of some short slotted holes, or just some slotted holes. You see in these web angles, we have horizontal slots. And those are here so that, say we have a whole bunch of beams that have about the same web thickness, very, very close to the same web thickness. They can vary because the beam size is a little different, or just due to the tolerance of in the thickness of the web. If we have these slots, then the fabricator can create a bunch of these angles in the shop with the same dimensions, and they'll work on all of those different beams. So this is a good example of when to use slotted holes there. Okay, similarly, in this flange angle, you see that we have vertical slots, and that's to deal with the variations in the depth of the beam. So the fabricator can use these to consolidate the number of angles that have to be developed there in a shop. Okay, so let's talk about the strength of these bolts. First, let's see how we calculate the design tensile strength of one bolt, phi times lowercase r sub n. Now, lowercase r sub n, we're going to use or lowercase r, we're going to use to represent the per bolt strength. This is a term that's used in the manual a lot. I don't think it's ever used in the specification. Okay, so we go to the spec section J3.6 for the strength. Phi is 0.75 because this is one of those non-ductile limit states. The nominal strength is F sub nt times A sub b, and F sub nt is called the nominal tensile strength, and it's from the specification table J3.2, and it's in KSI. A sub b is the nominal bolt area, and we're not taking out any threads or anything like that. We're just taking the nominal bolt cross-sectional area for that. Finally, the design tensile strength is phi times F sub nt times A sub b. Okay, so we know that the bolt will fail at the threads when it's loaded in tension, so how do we take into account the net tensile area? Well, we're not going to change this area here over and over again. That would be more difficult. Instead, what the specification has in it is that this net tensile area is embedded in F sub nt, and that just makes it easier during design. Okay, the bolt, or the design shear strength of one bolt, shear strength now, is very, very similar, except now we have F sub nv there for shear, and this again, and F sub nv is the nominal shear strength from table J3.2, and just like for tension, the net shear area at the threads is accounted for in F sub nv, not in the area of the bolt. This is just to make life easier on us during design. Okay, so let's take a look at table J3.2. First column, we have the description of the fasteners. Then we have F sub NT and F sub NV. Okay, so you can see here the main thing we're looking at would be these group A, group B, and then C down below. In group A, you can see that we have one entry for N-type bolts and another one for X-type bolts. And you can see the difference in F sub NV for those two conditions. So we're going to be using 54 KSI a lot. Notice that the nominal tensile strength doesn't change because the bolt's going to fail at the threads either way in tension. Notice group B, same deal. It's just that the stresses are higher there, or the strengths are higher there. Note there's also these handy hints there if we forget what's in group A and what's in group B. You're looking at the bottom of this table, we see this more generic entry. There's two of them, the N one and the X one there too. And this is in terms of F sub U. That's so that if we have elements such as anchor rods, we can use these. Okay, now there's one footnote here, footnote B, that we should talk about for a minute. And it says this, for end-loaded connections with a fastener pattern length greater than 38 inches, F sub NV shall be reduced to 83.3% of the tabulated values. Okay, so what's that all about? So first, what's an end-loaded connection? It's a connection like this, which is from Design Guide 17, Figure 5.2. You can see a series of bolts in a row there, and the loads coming in from the end of the connection, from this end and this end. Now, in such a case, the bolts will not uniformly share the load P. The bolts near the end, each end, will get hammered more than the ones in the middle. So we need some way to take that into account. So the way the spec does this is for normal size connections, there's already a 0.9 factor embedded in F sub NV. Now, for longer connections, the effect is more severe. So longer than 38 inches, we have this additional reduction as well. Okay, so we have this to deal with. Now, just to be clear, in contrast, this is not an end-loaded connection. You see the loads coming in uniformly to all the bolts in this case. So that's an example of when we do not have an end-loaded connection. Okay, so let's move on to the connection slip strength. For this, we go for SC connections. For this, we go to the specification section J3.8. This is our nominal strength for connection slip, and you see we have mu times D sub U times H sub F times T sub B times N sub S. Now, we will define these one at a time. But first, let's talk about the phi factor, because this is a fairly unique limit state in that the phi factor is variable. In this case, the phi is 1 if we have standard holes, or if we have short slots with the load that's transverse to the slot. Now, by transverse, it means it's perpendicular or within 10 degrees of perpendicular. Okay? Or we have phi of 0.85 for oversized holes, or short slots parallel is what we call it, but really what this is outside that 10-degree limit for transverse. So we have that, 0.85. Now finally, we have 0.7 for long slotted holes, and it doesn't matter what direction the force is in for those. So our design strength will be this. It's just the R sub n with the phi tacked on there. Okay, so let's dig into these variables some. Okay, mu is the mean slip coefficient. That's going to depend on the faying surface. Now, for Class A in the spec, it's 0.3. For Class B, it's 0.5. So it's a pretty good size increase between there. Class A is just clean mill scale, and Class B requires some preparation. Okay, T sub B is the minimum bolt pretension. That's here, the minimum bolt pretension. So let's see that table, J3.1. It's here. And you can see the minimum bolt pretension is a function of the bolt size and the group and the group. So you can see for a 3/4 inch bolt, it's very common. For group A, this is probably the most common one. We would have 28 kips per bolt. Note here we've highlighted ones that have changed. Now with that minimum pretension, let's go back to our equation. No, we want to calculate the strength here, but we don't want to undershoot it. We really want the average pretension, not the minimum. So therefore, we have this D sub U factor, and it's this. It's the average pretension divided by the minimum pretension, and it's 1.13 in the specification. All right, so more factors. We have H sub F. This is an adjustment factor for the presence of fillers. So what's a filler? So imagine we have two W shapes that we're splicing, and one has a thicker flange than the other. We may use a filler in there to make up the difference. Now, so there may be a reduction in the slip strength because of those. So let's see what the spec says to do. It says if you have no fillers, or if you have one filler at an interface, we just have one, so we don't really have a reduction there. If we have two or more fillers there, then we have 0.85. Now this is two or more fillers at one interface, so we have 0.85 for that. Finally, we have the number of slip planes here. Okay, so with that, let's just have a quick comment about slip critical connections. These are expensive compared to bearing type connections because of the surface preparation, especially with Class B, and the tightening procedures that are required and the inspection requirements. Okay, they're not needed for typical shear connections and most moment connections. They may be needed for dynamic or vibration loads. They also may be used to control drift in frames. Also, they're required for some moment connections, especially for seismic. The bottom line here is that we don't just want to use these as the default and throw them on the drawings everywhere, like I've seen before. We want to use these only when we need to use these. Okay, so moving on. Sometimes we have conditions like this where we have the loads on an angle, say, and these bolts are in combined shear and tension. And there's interaction between the shear and tensile stresses. Okay, so we need to check bolt shear and tension interaction. So here's our curve, our interaction diagram. On the x-axis, we have our shear stress, F sub RB. On the y-axis, we have our tensile stress, F sub RT. And the interaction curve for this would be this dash dot curve like so. Now, to simplify matters, in design, in the specification, this is limited at the top by phi times F sub NT. We would call that the available tensile strength, or in terms of KSI. And on the x-axis, we can't go any farther to the right than phi times F sub NV, which we would call the available shear stress. Okay, so and then we have this line along here, this sloping line. So the spec has a design criterion that's based on this. So let's see what we do with that. Okay, so we actually have two parts to this. First, we have that the required strength per fastener cannot exceed phi times FNT primed, which we'll define in a minute, times A sub B. Then we have a criterion for the shear. We have the required shear per bolt can't exceed phi times FNV times A sub B. Or if we want to do this in terms of stress, we divide through by A sub B and we get this. F sub RV can't exceed phi times FNV. Now, coming down here, of course we have phi of 0.75. This F sub NT primed, I would think of this as the nominal tensile strength in the presence of shear. So you see what we have here. We're basically taking this flat line and this sloping line and putting it in an equation form like this. This linear equation here, or expression here, that corresponds with this sloping line. And this limit up here, F sub NT, that corresponds to this flat line up there. So we kind of just laid it out that way to make it pretty easy to use. Okay, so one last little comment. Notice because we divide through by AB there, if we need the required shear stress to go in here, that's just R sub UV divided by the area of the bolt. Okay, so we have three different diameters that we're going to be using over and over again. So we should talk about those for a second here. First, if we go in the specification section B4.3b, it says for all hole related limit states except tear out, we're going to use the effective hole diameter. Or if we have slots, the effective dimension for the slot. And this is going to be for the diameter, we're going to call this DH primed, just to give it a name. It's the nominal hole diameter plus a 1/16 of an inch. This extra 1/16 of an inch is accounting for the loss of strength due to the damage around the hole from the hole forming process. If for tear out, we use a different diameter. Here we use the nominal hole diameter D sub H. For bearing, we're using the bolt diameter because this is all about the bearing pressure or contact pressure. So we have the bolt diameter for that. So we have three different diameters that we're going to use. Okay, so with that, let's talk about bearing and tear out. First, what's a bearing failure? Imagine we have a case like this. We have load like so. This is a bearing connection. The bolt has got some high contact pressure here, bearing pressure, and it's sort of squashing the material on the edge of the hole. Okay, with a tear out failure, it's different. With a tear out failure, we have a shear plane that occurs here and over here, and each of those will be at 0.6 times F sub U. And basically, we're tearing out this piece of the plate. So let's see a picture of this from a lab specimen. This bottom picture, you see a bearing failure, and you can see what's happened here. We have this from this high contact pressure down here, the steel's kind of piling up in this region, and we're getting some high deformation. For a tear-out failure, you can see one getting started here. You can see that these shear planes are getting started there and there, and if the test went further, it would tear all the way through and just tear this piece down on in the downward direction on the slide. Okay, so how do we check these? So we're going to go to the specification section J3.10, and we're going to use the set of equations for this condition. For standard oversized and short slotted holes where deformation at a bolt hole is a consideration. This will be our typical condition, so we're going to use it. So the bearing strength per bolt, note the lowercase r, is 2.4 times the bolt diameter, D, times the thickness of the connected part, times F sub U for the connected part. Okay, the tear out strength is R sub N, and we have two of these 0.6 factors, so we have 1.2 times L sub C times T times F sub U. Now, L sub C is the length of this shear plane. So, for example, here, it's in the direction of the force. So, at an edge bolt, it would be the distance from the end of the part there over to the edge of the hole. And here we use the nominal bolt diameter. Okay, for an other bolt, the one that's not at the edge, the L sub C is the clear distance between the holes. That's the length of our shear plane L sub C. All right, so now with that, ready to talk about our newly clarified method. That's a combined check for bolt shear rupture, bearing, and tear out. To read about this a little, you can go to the specification section J3.6. There's also a little blurb about this in the 14th edition specification section J3.10. Actually, there's a little more information there. In this method, we're going to calculate the effective strength of each individual fastener and assign that to the variable r, lowercase r sub n. So here, for one of the fasteners, we're going to have the minimum of the strength for bolt shear rupture, bearing of the first connected part, tear out of the first connected part, bearing of the second connected part, and tear out of the second connected part. Calculate all these, gather them up, take the minimum, and assign that as the effective strength of the fastener. We do that for all the fasteners. It seems like a big check, but in the traditional way, we would have checked bolt shear rupture, and later we checked this separately and then this set separately. So really, we're taking three checks and rolling them into one. And this is much more rational, by the way. Okay, so we calculate this for each of the bolts and we add them up, and that's the strength for the connection for this limit state. This is the nominal strength. To get the design strength, we apply the phi factor 0.75 because all three of these limit states, bolt shear rupture, bearing, and tear out, have a phi of 0.75. Okay, so let's do a little example of this newly clarified method. Okay, so in this case, we have double angles. They're 1/4 inch thick, A529 grade 50, and they're bolted to a 5/8 inch plate A36. We have 3/4 inch grade A325N bolts, standard holes. Okay, the first thing is I'm looking at that thinking, well, might not have that one memorized. So let's go look and see what the properties are. Go to the manual, table 2-5, and you see that we have F sub Y is 50, F sub U is 65 KSI. So it's really cool. It's the same as A992, so it's very easy to remember once we see it once. Okay, so let's start off by calculating the bolt shear rupture strength, and this is going to be the same at each bolt. It's going to be F sub NV times A sub B. So for a grade A 325 bolt, the F sub NV is 54 KSI. The area of a 3/4 inch bolt is just pi times 3/4 inch squared over 4, which is 0.4418 inches squared. But here we have two of these shear planes at each bolt. This is a double shear connection, or a double shear condition. These bolts are in double shear. Okay, so calculate this, we get 47.7 kips. And this is the strength at each bolt for bolt shear rupture. Okay, angle bearing. This is going to be the same at each bolt. 2.4 times the bolt diameter times the angle thickness times 65 KSI, that's F sub U for the angles. And we have two angles at each bolt. So we have one there and one there. So we have 58.5 kips from this. Okay, so angle tear out, that's going to be different at bolt A and B. Bolt A is tearing out the end, B is tearing out between the bolts. So at bolt A, the length of the shear planes are 1.25 inches here, minus half of the hole diameter. And the hole diameter, if we use the nominal, 13/16, so half that is 13/32. So subtract that out, we get 0.844 inches. Okay, so plugging that in here, we get 32.9 kips, and that's the tear out strength for bolt A. Again, that's tearing out like through here to the end of the angle. Bolt B is tearing out between the holes. So we need a clear distance between the holes. That's going to be 2 inches minus a half of a bolt or hole diameter here and a half of a hole diameter over here. So we have an entire hole diameter coming out. So we have 2 inches minus 13/16 or 1 3/16. And plugging that into our equation, the tear out strength of bolt B is 46.3 kips. Okay, moving to plate bearing tear out, same calculation, so I'll just give us the answer. For bearing, it's the same at each bolt, 65.3 kips. We have tear out at bolt A, it's 51.7, and it's tearing out this way now. And tear out at bolt B, 36.7, that's tearing out the end of the plate there. Okay, so we gather all these up. So we calculate the effective strength for bolt A, just gather all these up, take the minimum, 32.9 kips, and that's the effective strength of bolt A. The effective strength of bolt A, or bolt B, same deal, gather all these up, take the minimum, 36.7. Okay, so we have these two that control. Now we gather them up, and we add the two together, and that's the nominal strength of the connection for this limit state. Now, if we were to take this specimen as a specimen in the lab and load it up to failure, we would expect to see angle tear out here simultaneous with plate tear out over here. Okay, so the design strength for this limit state is 52.2 kips. Okay, so this is our newly explained method, and it's a very rational method, so it's pretty cool. Okay, so hole minimum spacing and edge distance. Let's spend a little time on that. Okay, so go into to the specification section J3.3. We find the minimum spacing requirements there. For a standard oversized or slotted hole, the center-to-center spacing S can't exceed, or must exceed, or must not be less than 2 2/3 times the bolt diameter D. Note there's a user note there that says that 3 times D is preferred. Also, there's a requirement in this section that the clear distance between holes or slots must be at least the bolt diameter D. Finally, just note here that this is typical practice for small, regular to smallish bolts to use a 3-inch center-to-center spacing. That's very common. Okay, edge distance table, or minimum edge distance, table J3.4 provides this. It provides the minimum edge distance from the center of a standard hole to the edge of the connected part. And you can see it's just a function of the bolt diameter, like for 3/4 of an inch, for example, our commonly used bolt. we have 1 inch minimum edge distance. Note that we need to do something for slots or oversized holes, and the table helps us there by pointing us over to table J3.5, which gives increments that we can add to these for these other kinds of holes. Okay, so now for that, let's move on to basic fillet weld related limit states and detailing. Finish off our session 1 with this stuff. Okay, so fillet weld rupture. We calculate the strength of that using the specification section J2.4, and here's our design strength equation. If phi r sub n is phi times F sub n W, which is the nominal strength of the weld in KSI, times A sub WE, which is the effective area of the weld. Okay, phi is 0.75 for weld rupture, because this is one of these non-ductile limit states. The weld strength, as you can see here, is 0.6 times F sub EXX, and this is the basic strength. Now, F sub EXX, we're going to have the weld metal tensile strength in KSI going in here. So this is essentially 0.6 times F sub U for the weld material. Now, this factor over here accounts for the fact that welds are stronger if you load them at some angle, not load them parallel to the weld longitudinal axis. Okay, so let's dig into that factor a little bit and see what's going on with it. Okay, so this factor is from equation J3.5 or 2-5, and let's see what happens. If we have a theta of 0 degrees like this, then the weld strength equation reduces to the form shown here. We have 0.6 times FEXX, and then the factor is just 1. Okay, jumping down to the bottom, if we have a theta of 90 like this, where the load is perpendicular to the weld, then this term turns into 1.5. So we have a 50% increase in strength compared to the case with the load parallel to the weld. Okay, so you see in between here the theta of 45 degrees. The strength is somewhere in between the two. Now, there's no free lunch, so what this means is that if you go look at the load deformation curves for theta of 0, what you'll see is that while the weld's weaker in that condition, it's more ductile than for this case. So for this additional strength, we have less ductility. So we have to take that into account sometimes. And a really good example of when to take that into account would be this special case that's in specification section J2.4, subsection B and note. And this is for a weld group where some of the elements, some of the welds in the weld group are loaded with a theta of 0. That would be like this one and this one. Those are longitudinal compared to the load. And the strength of those we'll call R sub NW and then L for longitudinal. And also in this weld group are stronger but less ductile welds like this one that has the load is transverse to this weld. Okay, so these have different load deformation behavior. So we can't necessarily just add the strength for each of them together. We need to do something special to take into account this sort of mismatch in the load deformation behavior. Now let's see what the specification says to do. Here's what the specification says. It says take the max of these two expressions. First, we can take R sub N WL, the longitudinal ones, just add it to R sub N WT, the transverse. Now, theta is 0 in this calculation for both of these going in here. You see here for theta of 0. Now, theta in reality for this guy is 90 degrees, but we add them together like that. Now, the second thing we can do is set the transverse weld at its maximum strength, or at its actual strength, 1.5 times R sub N WT. Now, this is because of the factor from the previous slides that has theta in it. The thing is, though, you can't just add R sub N WL to that, because you would need to have a larger deformation to develop all of R sub N WL. And the spec committee tells us that we can only use 85% of R sub N WL along with this full strength of the transverse weld. Okay, so you see how we must be cognizant of the fact that the transverse welds are less ductile. All right, now with that, let's talk about the effective area of the fillet weld, of a fillet weld. And you see here a fillet weld connecting a couple of plates. They're lapping there, and the weld size we will denote as lowercase t. And we're going to assume that the weld's going to look something like this. It may be more convex than that, but it's going to look something like this. Now we're going to assume that it's not assume. The design model is that the weld fails through the critical section, which is going to be the minimum section through here. The minimum section through the weld like that on this 45-degree angle in this case. Now the width of that critical section we call the effective throat, and we'll call it T sub EFF in our work here. This T sub EFF, just from trigonometry, is 0.707 times T. Now, if we were to have a welding procedure that we have shown will build out the weld farther, larger than T sub EFF, larger than 0.707 T, then we can use that larger value. Okay, so the weld effective area then is just the length of the weld times this effective throat distance. With that, let's derive a very handy number that we can use to speed up our weld calculations. Let's calculate the strength of a weld that's loaded at 0 degrees, so this is the weakest case. It's a 1/16 size and 1 inch long, and it has our most common weld material, the 70 KSI. Okay, so our strength in this case will be phi of 0.75 times the F sub NW, which in this case is 0.6 times 70 KSI, and times the effective throat, 0.707 times the 16th, and times the length, 1 inch. From that, we get 1.39 kips, 1.392 kips per 16th size per inch long. And this is very handy because then we can scale this number up for other sizes that are used in reality. And we're going to use this all over the place in our course. Let's do a little example just to show the usage. Let's say we're going to make it a little more complicated by having a theta of 90 degrees and and then we have a weld size of 1/4 inch, a realistic weld size, and 5 inches long. And here we have 70 KSI electrodes. Just to be able to write an equation for this, rather than having a number like this, let's write the equation like this. Let's call the number of 16ths capital D. So we have phi RN is 1.392 times D times the length of the weld. Now, because we have a theta that's not 0, we need to have this factor in here that takes into account the direction of the load compared to the weld. Okay, so going in here, this factor comes out to be 1.5 in our case because theta is 90. So we have 1.392 times 1.5 times 4/16 because we have a 1/4 inch weld times 5 inches long. And that gives us 41.8 kips. And that's a lot faster than just using the longhand equation that would look more like this. So it's just easier to use, less likely to make a mistake. Okay, minimum size of fillet welds. If you go into table J2.4, we have a list of the minimum sizes of fillet welds that we must use. And you can see it's based on the thinner part that is being connected. So for example, if you have a half inch part and that's the thinner part being connected, we need at least a 3/16 inch fillet weld. Now this requirement is to minimize the effect of that a thick material would have on welds that are not large enough. Because if we have very rapid cooling, then we may have a loss of ductility in the weld. Also, if we have thick material compared to the welds, their restraint may result in some cracking in the weld. So we don't want either of those. So we need to satisfy this table right here. Okay, next, what about the maximum fillet weld size? We go into section J 2.2b for the maximum fillet weld sizes. And this applies only along the edges of material like shown in this diagram. Imagine we have two plates. We have a plate here and a plate slapping on top, and the thickness of the plate is T sub P. The rule is this. If we have the T sub P that's less than 1/4 of an inch, then the maximum weld, T max, is just T sub P. So we can build this all the way up like this. Okay? If this plate T sub P is thicker, then we need to hold this down 1/16 of an inch. So the maximum thickness of the maximum size of the weld will be the thickness of the plate minus 1/16. Now the reason for this is that if the welder welds too high on this, he can eliminate this corner. And what will happen then? Imagine you're looking down at this. You can't tell where the weld is starting and ending. So you may have a weld that looks like it's based on the apparent edge that's left, or the apparent corner that's left. It may be that the weld looks like it has a larger effective throat than it does. It may not have the effective throat that we use in design. So we want to hold this down 1/16 of an inch to leave this corner intact. Now, with smaller plates, we're likely to get the effective throat that we want anyway. So it doesn't matter there. This is sometimes called undercutting the upper plate. This is what we're trying to avoid there. Finally, one bit of confusion that happens sometimes is this limit it only applies to edges. It doesn't apply to a condition like this, like a T-joint. It does not apply to that. As far as this requirement goes, we could have a huge weld there. We have other practical considerations that will stop us from having an enormous weld. Also, we have the next thing, which would the base metal strength that would prevent us from using a huge strength that we would calculate there. Now, not only do we have to check the weld strength, we must also check the base metal strength at the fillet weld. Now, to find the procedure for this, or the provisions for this, we first go to table J 2.5 in the spec, and it points us to section J4 for the base metal strength. Now, this check is traditionally done with the shear strength, so we go to section J4.2, strength of elements and shear, and then we get this equation using the shear rupture equation. This is the design strength for base metal strength, and the only thing that's a little weird here is this A sub GV. We usually have an A sub NV for shear rupture, but in this case, the shear area of the element at the weld never has holes there, so it's always going to be a gross area, so I stuck a G in there. I think it's clearer. Now, F sub U is the tensile strength of the base metal, and phi is 0.75 because we're checking shear rupture. Okay, so let's do a little example. In this case, we want to calculate the design strength. We have a couple of plates. Each has A36 steel. Each is of A36 steel, and F sub U is 58 KSI. All right, the top plate is 5/16 of an inch thick and 5 inches this way. And the other plate is 3/8 of an inch thick. The welds are 1/4 inch size and 5 inches long, and we have 70 KSI welds. Okay, first the weld rupture strength. We have the 1.392 kips per 16th size per inch of length. So that shakes out like this. We got 1.392 times 4/16. There's 4/16 there. Times 5 inches long, a 5-inch long weld. And then we have two welds, one there and one there. In this case, the load is parallel to the weld longitudinal axis, so we don't have any increase here from the directional factor. So we get 55.7 kips for weld rupture. Next, base metal. Let's exercise the equation from the previous slide. Here we have phi is 0.75, 0.6 times 58, which is the F sub U for the plate, times 5/16. We know this one controls because it's thinner than this one. Times 5 inches. Note here, the length we use for this check is always the weld length. So if you slide this back a little bit where we have a gap there, we would still use 5 in this calculation. And then we have two of these lines. We have a failure along here and a failure along there, so we have two. This comes out to be 81.6 kips. So in this case, the weld rupture controlled and the strength is 55.7 kips. Note we only check these two limit states here. There are others that would apply in reality. Okay, just finish up with a comment about something we can be thinking about. Pretty simple during design is the effect of the number of passes and the fillet weld size. Let's say we have a 5/16 fillet weld. This can be laid down with one pass. Okay, now if you have more passes, it's obviously the price is going up, the cost is going up. So let's analyze this for a second. Look on this plot. On the x-axis we have the leg size, like 5/16 in this case, and on the y-axis we have the number of passes, and this is directly proportional to the cost. Okay, so for 5/16, and we have one pass, so we're here. We have one pass, 5/16. Now say we double this size from 5/16 to 5/8. We double the strength. We go from 1 to 2 there. But look at what happens to the cost. It takes 6 times more passes, or about 6 times more cost to make that weld. So you can see that's a lot to pay for double the price. You see also there's a big jump going from 5/16 to 3/8. Also, 3/8 requires 3 passes, so it's about 3 times more expensive. We only got a little bit more strength. 3/8 divided by 5/16, so just a little bit more strength there, but it costs 3 times as much. So this leads us during design for decisions such as, imagine I can make the weld a little bit longer, and then I can get away with going from a 3/8 to 5/16. Well, it's a no-brainer there. So we need to be cognizant of this. 5/16 is kind of our magic number, and the price really goes up after that. Okay, with that, that's the end of session 1. Thank you all for attending. Now, next Wednesday, we'll have Fundamental Concepts Part 2, and you can see the topics listed down here. And with that, I'll hand it back to Nate.
All right. Thank you, Brad. So we're going to go ahead and have a question and answer time here. But first, we have a couple of polling questions that we're going to pose to the audience to test whether they were paying attention. So we'll go ahead and go to those polling questions now, and here is the first one, and this is a true or false statement. So true or false, when checking tear out at a bolt hole, one should use the nominal diameter of the bolt hole plus a 1/16 inch when determining the clear distance. Is that a true or a false statement? And you can select the answer you think is correct on your computer screens, and we'll look at the results together. All right, again, that statement is, when checking tear out at a bolt hole, one should use the nominal diameter of the bolt hole plus a 1/16 inch when determining the clear distance. It looks like most of the answers are in, so we're going to go ahead and close the poll. Now, Brad, the audience thinks that about 2/3 of the audience thinks that that answer is true, and about 1/3 thinks that that is false. Who got it right?
Well, the 1/3, because the extra 1/16 is only used for the hole related limit states other than tear out. We use that extra 1/16 for checking limit states like tensile rupture, block shear, shear rupture. We check, or we use the extra 1/16 for that. For tear out, we use the nominal hole size. Now let's go back to our slide where we mentioned this, because I can click one of the slides, right?
Yep.
Okay. So go back to here. So we said that for tear out, we only use the nominal hole diameter, D sub H. Nominal hole diameter. Now you can see in our calculation, we have an example of this here. And you see that in this case, we're checking tear out of the angle. And so for bolt A, we need L sub C is the distance from the end of the angle to the edge of the hole. And you can see here we have the nominal hole for a 7/8 inch bolt. The nominal size of a standard hole there is 13/16 of an inch. So you see here we're taking out half of that to go from the end of the angle to the center of the hole. We're taking out half of 13/16 to get to here. And you see likewise down here at the bolt B, we're trying to get the L sub C is the distance between the right edge of this hole to the left edge of this one. So we have 2 inches minus a half of a hole diameter there and half over here. So it's minus 13/16 total. And notice again, we're using the nominal there. All right.
All right. Well, let's go on to the next polling question and see if folks can get that one. So the question is as follows. When determining the strength of a concentrically loaded fillet weld, which of the following loading angle theta gives the greatest strength? Is that A, 0 degrees, B, 45 degrees, C, 90 degrees, or is it D, the strength is independent of that angle theta? Again, the question is, when determining the strength of a concentrically loaded fillet weld, which of the following loading angles theta gives the greatest strength? All right. Looks like the answers are coming in a little bit slower, so let's go ahead and see what the results are here. So Brad, on this one, it looks like almost 90% of the people out there think that this answer is C, 90 degrees. Did they get that one right?
Yes, that is correct. So you can go back to our equation for the weld strength, and you see our directional factor in parentheses, and it's a function of the angle. And so if we have 90 degrees in there for the angle, for that factor, if we have 0 degrees, we only have 1. So yes, that is correct.
All right, good job everyone. So let's go ahead and move into some of the questions that came in from the audience during your presentation, Brad. And we'll go ahead and start off with a question posed on slide 27. The question is, do moment connections apply on the weak axis? Now the speaker doesn't, or the question answer doesn't specify whether they're talking about the column or the beam, but they're asking if moment connections apply on the weak axis.
Well, I'm going to assume that the participant is referring to a case like this, where we have the connection into the weak axis of the column, the minor axis of the column. And absolutely, you can certainly have a moment connection to the minor axis that puts the column in minor axis bending. In this case, we weld the flanges of the beam to the stiffener at the top here and at the bottom there. So if we have a moment here, say we have a negative moment into this beam, that would turn into a flange force up here pulling this way, and flange force down here pushing this way. And those forces would go through the stiffeners into the column flanges using fillet welds or penetration welds there, and that would transfer the load effectively into weak axis bending in the column. No problem there. Now, weak axis of the beam, that's a different question. But I'm assuming the questioner is not referring to that.
All right. Let's go ahead and go to slide 38. So, a question about the A307 machine bolts. What are typical uses of these bolts for structural steel connections when one might run into A307 bolts?
I would say very infrequently. I don't know that I've ever used one of those in a real job. Maybe some very, very small platform or part. That's about the only application that I can think of. There may be others, but that's all I can think of right off.
All right. Question about bolt tightening. This question asker states, I understand RCSC discourages torque charts in determining acceptable bolt tightening requirements and specifies the methodologies you describe herein. Can you briefly explain why this is so?
Well, the relationship between torque and the axial load in the bolt is highly dependent on the friction in the threads. And you can see that 3 of the 4 methods here still use the general method of going from torque to axial force, but they're very particular methods that are established and are just they're just well documented, and they're prescribed in the RCSC spec. For example, with the calibrated wrench method, I've read that the inspection requirements on those are such that it's pretty often. It's a lot more often than one would think. So and then also for these twist-off bolts, they have to be taken care of in a particular manner on site to ensure that we have the right coefficient of friction there at the thread. So while the idea of indirectly getting the axial load we want using torque is it's just a bit indirect, but we do have these 3 methods that do use that method. Note the direct tension indicator is kind of the other way around. It's using the axial deformation to directly measure the deformation of those little nubs is in the same direction as the axial force. So it's a more direct measure.
All right. Let's move on. On slide 48, the question, when should you specify oversized holes?
I really can't think of a time that I've done that. I've almost always used either standard or short slotted holes, and every now and then we have a really weird application, and we'll have some hole that's longer than the long slot on here. I guess if your situation seems to dictate it, then use it. I can't think of an example right off the top of my head. There's probably some, but it's just not coming to me.
All right. Let's see here. Let's go to slide 58. So thickness of fillers are taken into account. When would you see more than one filler used in an application?
I have not seen that, but it certainly must be possible, or else they wouldn't have put it in here. I would imagine that this would happen if you just had the gap that you need to make up it's just going to be conveniently made up with more than one filler of thinner thickness than the total gap. So it's just going to be on a case-by-case basis, and I've not personally seen that.
All right. So here on the slide talking about bearing and tear out, there's a question about this idea of deformation at the bolt hole. Can you discuss when deformation at a bolt hole is not a significant issue and the higher values can be used that are given in this section of the specification?
Okay. The only time I've seen that, I would need to pull up the AISC design examples to be sure. I think in the and verify this before you run with it, as I'm going from memory here. I think the extended shear tab design example, I think one of those uses that, and they're trying to get the extra rotational capacity there. But go research that before you run with it. And that's the time that I can think of right off the top of my head.
All right. Next question. So here talking about spacing of bolt holes. Can you clarify what is meant by the clear distance between the holes versus S, the spacing.
Okay, S is the center-to-center dimension, whereas the clear distance is the distance between the bolt holes. Imagine you had a couple of slots, and the slots are, they're beside of each other, and the slots are turned such that you don't have a whole lot of steel left between the slots. In that case, we would still have this clear distance requirement that would save us from putting them super close together.
All right. Let's see here. Here's a question on slide 70. Also sort of getting at this idea of hole size and the sparing and tear out checks. So on slide 70, how do we get 13/32 in the angle tear out for bolt A?
Okay, well, comes from this. Take a look at the L sub C is the distance or the length parallel to the load of the shear plane at of the shear failure. Now that's going to be measured from the end of this angle parallel to the load over to the edge of the hole. Now what do we know earlier than that? Earlier than as far as the dimensions, we know that the end distance to the center of the hole, and this should be to the center. It's kind of pushed off a little there on the screen. The distance from the end of the angle to the center of the hole is 1 1/4. We want to back off a half of a hole diameter, or 13/32, to get to the edge of the hole. It's just that the 13/32 is just half of this. Okay.
All right. Well, thank you very much for the answers to those questions, Brad. Unfortunately, that's all the time we have for the live question portion for this session. But if we received questions from you, or you submitted questions to us rather, that we didn't get to here in this live session, do know that we received those questions, and we will work with Brad in the coming week to respond to those question askers via email. So we thank you for those questions. For those of you that register for the 4-session package, you will be receiving PDH credit at the end of the entire course. PDH credit for 4-session registrants will be awarded on one of two criteria. Either one, your attendance of the live session, and we'll have record of that attendance, or two, based on your viewing the session video recording and passing the associated quiz. The video and quiz for a given session will be available to 4-session registrants by the end of the day on Friday after the live session. And you will get an email from the address webinars@aisc.org notifying you when those are available. You will also have access to that quiz and recording for 4 weeks after the live session. Certificates will be distributed to the 4-session registrants after that last quiz period ends. So that will be the week of December 16th that PDH certificates will be sent out for 4-session registrants. And those 4-session registrants can find all this information, all the handouts, quizzes, quiz scores, recording access, and attendance information on the website by signing in at aisc.org, going to your user profile, and then to the bottom of that page at Course Resources. Simply select the course you are enrolled in, and you'll see a screen that looks like this with all that information for this course in one place. Also want to let you know about our ongoing night school course that has started recently here. Our 21st run of night school is the course Welded Connections, a primer for engineers, taught by Dwayne Miller. This season kicked off on October 8th, and so 2 sessions have gone by, but there is still 1 more week to register for the 8-session package of this excellent course. With an 8-session package, you'll be able to catch up because you'll have the recordings for the first 2 sessions. And if you are one of our 4-session registrants for this webinar series, you'll be able to get a $150 discount by registering for the 8-session package for that night school. Alternatively, you have the registration option to register a group on a session-by-session basis for any of the upcoming courses, and you can see a list of those courses from this night school here on your screen. For more information on this course and how to register, you can visit aisc.org/nightschool21. And that pretty much does it for today. In a moment, the session is going to officially end, and a survey will pop up on your screen. Please help us out by completing our survey form. It's very short but very helpful to us in improving this type of continuing education programming for you all. Thank you for Brad Davis for presenting to us today, and thank you all for your participation. Enjoy the rest of your week, and we'll see you for the next installment of this AISC webinar series.